Okay, I think I'm just very sorry to say, like the past 2 days, I couldn't able to, I couldn't able to handle your class. I was in some workshop, so that's why. From today onwards, we'll move on to, regular class. So on that day, I just gave a little bit introductions about what all those things are. Just roughly, I will revisit and then I will get back into the syllabus. Okay. So right. So in this course, we are just going to read about computer architecture. Okay. And parallelly, right, you have a lab called computer system design lab. Because you have this lab. I don't know whether you people are going to come, but suppose, I mean, anyhow, right, you need to do it, and this is the equivalent lab for this syllabus. So now, right, when you just if you go with us, for this course, so there might be a prerequisite. The prerequisite is, it is all about computer organization. So you have read about computer organization, and it is a prerequisite for both the cases, even for computer architecture and for computer system design. I won't say that in case of computer architecture, maybe right, like 30% we may involve computer organization. But when you go with the computer system design lab, so I can say right, 70 to 80% of the lab we are going to explain with respect to the knowledge what you got, what you acquired on computer organization. So this is going to be the prerequisite computer organizations, and in general, right? So what you read on computer architecture, computer organizations. Before that, what makes the difference? So CA versus CO. You read CO, and now you are going to read about CA. But because previously, right, the previous previous syllabus and all, we have like common computer organization and computer architecture as a single subject we have, and they separately read about microprocessor and microprocessor and microcontroller. But in your case, right, it has been into two different subjects. So altogether, all has been combined, and they made it as CA and CO. So what is that difference? What is CA and what is CO? So what you read in CO and what you are going to read in CA. In general, when you talk as like computer architecture, it is above computer organization. Because when it just normally, right, we have so you have an applications, and you have some system softwares. I mean, it may be like this, right? And below that, right, we have a hardware. Normally, right, when you take any systems, it will be like this. CO is something here. So, CO, when you talk as computer organization, it is all about how it does. Okay. Here, right, CA is something between this and this. Okay, system software and the hardware. So that is the C way. So what it does, what the computer is does, and how it things. Okay, so that's the basic difference. Because previously, right, you learned about digital. So in case of digital, you know how to design a circuit. Okay, so once you design a circuit, how about the data flow, path, all those things? I think the pipelining, those things you have read in CO. Okay, so now how to do this with the help of this hardware? What can be achieved? So that, right, we are going to read in computer architecture. Okay. So this is the base things. So before this, let me brief for something like what is microprocessor, what is microcontroller, all those things. Sorry. Because we people are frequently hearing this word like what is microprocessor, and the one more word is microcontroller. Because I don't know whether you know it or not, but you have to be thorough, like microprocessor versus microcontroller, RISC versus CISC architecture, and the examples. So you should know all those details. Okay. So first, right, what is the base difference between a microprocessor and a microcontroller? So let me take our laptop. Am I with you, guys?
Yes, ma'am. Yeah.
Yes, ma'am.
Yeah.
Yes, ma'am.
Okay, ma'am. Okay. So just we will take our laptop or a desktop systems. Okay. So what we are trying to do, oh, I know, right? We are executing all classes of applications. Are we restricting that you should run this or you should run this? We are not doing it, right? We are going with any audio applications or video applications or our own applications, programming. So we are doing everything. Okay. So when you talk as microprocessor, so clearly, right, it is a general purpose, which means we can use it for any activities. Okay, so when you talk as microprocessor, it is going to be a general purpose device. So on the other hand, when you talk as a microcontroller, so let me take an example of washing machine. So what it does actually, washing machine, okay, let it be so something that we are just pouring your solutions, then right it will soak it and then rinse, spinning, and then only this is the thing that it is regularly it is doing it. Or else you take a projector, I mean example, some project LCD projector you have. So what it is doing? So the role is right. Whatever the inputs we are going to give, so taken up that input and it is trying to project it through the LED or LCD. So this is what it is doing it, right? So ultimately, right, what the functionality it does. Can you say is it doing a specific function? Because whatever is meant to do with microcontroller, only it is doing that task. Is it doing any other task? Or when you go with an LCD projector, so the same thing it is doing, or a printer, or you just take those things. Or else, in a nutshell, what we can say is when you take as a microcontroller, it may be suitable for a specific applications. This is first. Got it? So this is what a when you take as a microprocessor, it is going to be a general purpose. Think as your desktop or like whatever it is, or like even to a supercomputer, whatever it is. Okay, it is going to be a general purpose. But when you take as a microcontroller, so it is going to be application specific. Okay, mostly right. It may be suitable for carrying out the specific applications. So that's why, right, most of the cases they may say as embedded microcontroller. When you talk as a microcontroller, they say it as embedded devices because what is the definition for embedded is this: it is meant to do a specific application. Since microcontroller is useful to carry out specific applications, probably right, the microcontroller will be suitable for any embedded applications. Got it? So the best that's what I mean. When I'm saying this washing machine or a LCD projector or a printer. Okay. So those are all the examples for embedded applications. These applications are involving the microcontroller. When you take this case, your laptop, a desktop, server. So those, sorry, okay, those are the example for the general purpose things. So this is the base. And move on to the second difference. The other major difference is you may have heard a word like off chip peripherals. Let me explain. And here, right, it is on chip peripherals. So what is that? Let me take. Suppose, right, when you take any microprocessor, do you think a microprocessor alone, okay, just think CPU. The CPU alone is enough to carry out your function in your laptop? Do you think you forgot about this? What is that? Screens and keyboard. Don't say those things. Is it essential to have a monitor? Without monitor, can we? I mean, can we visualize our case or not? think of your, I mean, think of forget about a laptop. You just you have you have our desktop systems at home, right? You have a monitor, you have a keyboard, you have a CPU. Do you think that monitor is essential, or can we replace the monitor with anything?
It is essential.
Is it essential? So can you project it instead of using monitor? Can we use a projector to do that or not?
Yes, ma'am. Yes,
Yeah,
ma'am.
you can do it. Okay, well, so it is not a mandatory devices. So those are all additional peripheral devices. But still, right? You know what is CPU? So as okay, currently we keep it in our mind. Arithmetic and logical unit is your CPU. So when you want to do, when you want to execute your program, what is the additional component you may require, or any other component or any other peripherals? Here, this peripherals is nothing but the devices. Here I put the word as peripherals, right? Do you think, right? Because okay, let it be. I am just have CPU.
Memory, ma'am.
Yes, ma'am.
Memory.
Yeah, memory. Okay, so you need a memory, right? It may be a RAM or it may be a ROM. Okay, so definitely, right? You need a memory. And other than that, I mean, in our school levels, we read about like memory input and output devices. I'm not going to speak about input and output devices because we need to go much deeper into that. Okay. So, right, other than this, the memory devices, we have a few more devices. In the lab part, we will see that we need a timer, we need an interrupter, we need a serial controller, some analog to digital controller. Okay, so many things. It not only a CPU things. So when you just think of this, so these are all the additional components that are essential for performing any functionalities. Again, I won't say that this is needed for all the applications, but right. So it may be needed. Depends upon the applications. It may be needed. So what they are doing in microprocessor is, if only CPU alone is there, okay, this one alone is there, and they are interfacing these devices externally with the CPU. Clear? CPU, because when you take as a microprocessor, only CPU alone is there. Okay, so whatever the devices we need, so these devices are interfaced externally with the microprocessor. That's why, right, I have just put the word as off chip peripheral devices. Okay, it won't be in the chip. So when the Intel is giving the processor, so it will be only the processor part alone be there. The remaining things has to be as externally interfaced with peripherals. It will be interfaced. We are making use of it. Don't think we need to do it, but it has been built it already. Okay, so this is microprocessor. When you move on to microcontroller, okay, so on the other hand, we have a microcontroller where I put the word as soft chip. Just now I have defined where the microcontroller will be suitable, where it is suitable.
In embedded devices.
Yeah, embedded devices. What embedded does? It is meant for what?
To do a
Only to
specific
do
application.
Specific
Yeah.
applications. Okay, it's a good. So it is meant for specific applications. So assume that I'm just going to run a program for a washing machines. I know, right, what devices I required for it. Do you agree that or not? I know how much memory it is going to use, because when I take a laptop, if I'm going to execute any applications, my video application may take larger memory, my audio application may take small, or if I'm just running a basic things, it may require only rest RAM. So I'm running various applications. So obviously, right, I don't know like what amount of memory I require to execute my applications. And since I execute variety of applications, again, which devices I need to interface is also a mandatory. I mean, it is also a question mark. But when I take a washing machine, I clearly know, right? I'm going to use. My program is only this much size. And moreover, right, whatever the program I'm once I dumped it, should I need to change it? Should I need to change it? Washing machine, okay, this what? So for like taking water, soap, rinse, water spinning, rinsing, all those things. It is this, right? It is a programmatically it is doing it, right? Is there any alteration are we going to do in that once it is get into the application?
No,
Are we
ma'am.
going to change anything? No, right?
No.
So clearly we know like what amount of memory it is required for our applications, what are all the devices we need it for that applications. So obviously, right, that's why right we need to choose a microcontroller for designing an embedded system, because when you take any microcontroller along with the CPU, got it? You have a CPU. This diagram, it may be, I think. It should be like this. So you have a CPU, and we need to interface externally all those things. But when you just go with microcontroller along with the CPU, you should, I mean, everything will be there. You have a RAM, you have a ROM, whatever it is, whatever we needed. ROM will be there, timer will be there, interrupt will be there, serial will be serial communication, ADC controller, all will be there. So this is microcontroller. But here, right, this part is microprocessor, and the remaining things we need to interface externally. And here, right, when you go with the microcontroller along with the CPU, all those things will be present, all their devices. That's why on chip peripheral devices, because this is the chip. Okay, in this chip we have all the peripheral devices, but in case of microprocessor, only this thing is there. Okay, I mean, I will differentiate. Only you have these things. You need to interface all those peripheral devices. Clear? So this is the basic difference between a microprocessor and a microcontroller. Any doubt in this? Shall I proceed? Hey, be response star.
Yes, ma'am.
Yes,
Yeah.
ma'am.
Okay. Now this, I mean, hope right you have been clear with this. And normally, right, since we are not onto that, but generally, right, whenever you are going to read any microprocessor or any microcontroller, you need to read about the first one is right. Normally, we will read this, the architecture of the corresponding processor, the pin diagram we need to know, and the instruction set, and the fourth one is interfacing. Okay, so these are the four major topics. It is very important when you are going to learn about the architecture of any processors. Okay, because here, right, when you learn about the architecture, literally, right, it is something like a programming model. Programming model in the sense, have you heard this word? Have you heard this word registers?
Yes, ma'am.
Yes, what is that? What is register?
Flip-flop. It will
Collection of
be
flip-flops.
store base.
Obviously, right, it is going to be
Collection of
collection of flip
flip-flops.
flops. So if it is going to be 32-bit, obviously it's a 32-bit 32 flip flops. So when you take as an architecture, it is all about a programming model. So programming model is, I mean, in turn, right, it is about the register organizations. Hope then assumption, you know this, isn't it? Yes or not? R not R15.
Yes,
Have you
ma'am.
read about these registers?
Yes, ma'am.
Yes.
Yes, madam.
Where? Something in ARM, isn't it? Okay. When you, I mean, the last CEO, right? When you learned about the ARM architecture, so hope you might have heard these words. So, because these is very very important. When it is important is whenever right you are going to write an assembly language programming, because now right we are living in a fantastic world. Without knowing what hardware we are working on it, we are executing our program. Do you agree that? Does anyone explore? Ah, I mean, I am working on Mac. I should write a code accordingly. Or I'm working on x86. I should write accordingly. Does anybody have that awareness in your mind? If so, most welcome. Does anybody have? At least now we just go and see our system properties, like what processor we are going to use. I mean, we are using it. Sorry, we are not. I mean, we are not look onto that, isn't it? Agree? Pala panna parada. You need to respond it, or else I will come and kill you. Are you working with respect to the hardware knowledge? When you are writing a programming using your C or C++, does your hardware comes into your mind that you are working for, or you are writing a code for Intel, or you are working a code for ARM? Do you have that? Are you doing that?
No, ma'am.
We are not doing
No,
it,
ma'am.
right?
No, ma'am.
No,
Because
ma'am.
who is doing? Something is sitting between this and this. Who is here? You and me, yeah?
Compiler.
Yeah, compiler is doing, because we are clearly writing a high level language. So compiler, it is taking it out and then it is converting to a assembly code or assembler. Okay, whatever it is. Okay, let it be. I'm generalize. So the object code. See, when you want to write something an assembly code, assume that I need to add two numbers. So what will you do? So let it be. Say for example, in 3000, the memory address 3000, I have a data like this, 0x12. At 3004, I have a other data x 22. Now I need to add the result and I need to place it here. I'm asking you to write an assembly language programming. So in high level language, very simple, right? Just you will start write it percentage t percentage t. You will get A and B. Sorry, okay, something here, you will add it and then you will print the result. That's it, right? Now the question is here. Okay, so now right, we need to get the data from here in this occasion, and then we need to add it. So when you want to write an assembly language program, right, it is hard, right? We should know about LDR. So we have to move the data which is there in the address 3000. Similarly, right, LDR, load the value R1 from the address 3004. And then, right, we need to add R0, R0, R1 something. Okay, so suppose, right, if you are asking you to write an assembly language programming or a low level language program, what you should know? What is needed here?
Registers.
Only if you know about the registers, that only, right, you can able to write a program. Yes or no?
Yes, ma'am.
Yeah, because I think that is very very important. Okay, so that's why, right, when you just go with the architecture of any processor, probably, right, we know about the programming model, which is in turn, right, it is all about the register organization of that processor. So only if you know this, probably, right, you can able to write an assembly language program. These two are contribute much for them for writing an assembly language program. One is you should know about the architecture, and the other one is you should know about the instruction set. Only then you can able to write the assembly language programming. So you people may have a doubt. Nowadays we are writing an assembly, I mean high level languages. Now what is the use of this assembly language programming? So where they are using it? So probably, right, since our people are getting onto the application side, what to say, placements, uh, we are not concentrating much with these subjects. That's the major problem. If some compiler design company or processor oriented company comes, then you may really realize the importance of these subjects. Okay, so most of the device driver programs, got it. So when you want to write a device driver, hope you know what is device driver, right? If you are installing any external devices, so probably, right, you may get a message like device driver installed. So it is a software or as an acting as an interface between a newly interfaced device and the OS. So still, right, most of the device drivers are written in assembly language programming. because assembly language program has the full rights to access the registers. Here, right, this code we are writing it. We are we restricting that this A and B should be stored in R0 or B should be in R1? Are we restricting like this in higher level language? Are we doing like that?
Oh, no.
We are not doing it, isn't it? But right, when you go with an assembly language, we can do it. We can do everything what we need. We should have a control because many things are there. Suppose, right, I'm just passing a function variable. Assume that I'm just passing a variable like a comma b. So when I'm passing it, but internally, right, it will go to the register R0 and R1. I mean, implicit. This has been defined. It. Even right when you read in C or C++, the staff might have told right when you are going when you try to avoid more number of arguments when you are setting it, try to avoid more number of arguments. Have you listened to that? Have you listened? Have you heard that word?
Yes, ma'am.
Why? Why they told like that? To avoid confusion. Huh?
Memory wastage.
Huh? So it is not about the memory wastage. See, what will happen
Because
is
local argument registers for local arguments is restricted, ma'am. That's why.
yeah, see, when you have this A and B, only two arguments can be onto the register. Suppose I'm giving C and D, where it goes is it will goes to the stack. It will move us to the memory. So again, you know, right, the fast of your processor and the memory is not the same. So memory speed is little bit lower than the memory device speed is little bit lower than the processor speed. So it may take some time, but if the time is in terms of milliseconds or nanoseconds, but still then right when you talk of performance aspects, these things has to get considered. Okay, so the advantage of assembly language programming is this: we have a privilege to access all the registers when you are working with the low level programming, but it is not possible with respect to high level program. Okay, so these two are important when you're just going to work with the what to say low level programming. You should familiar with the architecture and also you should know about the instruction set. The second thing is the pin diagram. So pin diagram. Okay. Pin diagram is like anything. So if we take a processor, assume that this is going to be an 8086 processor. So every pin diagram will have certain pins. Assume some 40 pins. So because some data pin will be there, some address pins will be there. So many pins will be there. So the learn of this pin diagram is, what is the need for learning the pin diagram is, if you want the processor or a microcontroller to communicate with outside world. Okay. Assume that we have only a raw processor with us, like nothing in that. I mean, the lab. Suppose we come to this lab, you have this opportunity to work. We have only the controller will be in our hand. So when you want to interface any devices, we need to interface. So when it is possible, only if you know the pin diagram of that processor or controller, then only right it will be easy for us to able to interface any devices. Okay, so that's it. That's the need for pin diagram. And another one is the interfacing aspects. As I told you, when you go with the microcontrollers, it will be already along with the processor, along with the CPU. So directly we can make use of it. But when you go with the processor aspects, we need to interface those things. Okay, so such interfacing mechanism should also be known. Like as I said, when you have a CPU alone, we can't do anything. Like what is the essential components we need? We need a keyboard, we need a mouse, we need to interface the monitor. All those things is needed, or we need a projector. Something is needed to get to know about all those things. So how to interface those kind of IO devices is also essential. Okay, so any processor or microcontroller. So these are all the core things that might be you should know. Okay, architecture, pin diagram, instruction set, and the interfacing. So according to our syllabus, uh, I think right since the syllabus is a little bit advanced, hope you read about the architecture, about the ARM processors, and you learned about the instruction set. The only thing is you haven't learned about the pin diagrams and the interfacing things. Okay. But in the lab, right, we will see a few controller spin diagram, and accordingly we will try to work it out. Now, right, you may have a doubt like what is there in our syllabus. So CO, I don't know what you read, but when you just go with the computer, till then it's clear for you. Shall I proceed?
Yes, ma'am.
Okay. So here, like a little bit confusing, but just listen what I'm saying. It basically, right, when you talk as any processor, normally, right, one is a risk, another one is the system. Okay, so what is risk is reduced instruction set architecture, and this is complex instruction set architecture. The motive behind of revising your syllabus is this, because like almost I won't say like over a decade, 10 years back, till 10 years, before 10 years, this has been popular. Like before 10 years. So CISC, right, it ruled the world. Almost like most of the processors are under the CISC category. It is complex instruction set computer. But nowadays, right, all the processors, they are trying to adopt the RISC architecture in the processor. Okay. So nowadays, right, whatever the processor that are existing in the market, so most of the processors are of RISC-based machines than a CISC based machines. So the best example for complex is this one. CISC is the Intel processors. Okay, all your Intel processors are CISC based machines. But even Intel is also trying to convert it instruction set to a risk-based instruction set. Still it is doing it, and they themselves has developed one ARM-based processor, something I think strong ARM. So which means right, even Intel is also onto a risk-based architecture. Nowadays they came into that risk-based architecture. Now the question is why, right? Why the all the microprocessor vendors have been moved to a risk-based architecture? So that is the very big question. So the actual answer behind this is when it is a reduced instruction set. One is the number of instruction is also less. So I agree. Okay, here the number of instruction class is reduced, and at the same time, the cycles required to execute the instruction cycles required will be fixed, and the length of the instruction is also fixed. This is very important. Okay. So when you just talk about a risk based, this or the cycle required, which means right, I can even say most of the instructions will take a single clock cycle. I told you only most of the instructions, not all the instructions will take a single clock cycle. So most of the instructions will be a single clock cycle. And when you talk as a length, right, a length is something you might have heard like 1 byte instruction, 2 byte instructions, 3 byte instructions like this, right? Because here, right, when you take an Intel processor, the instruction length it varies from 1 byte to 6 byte. But here, right, most of the instructions will be of 1 byte. Clear? Okay. So this is the one. And the next thing is, in case of risk, the number of registers will be more. Here, more number of registers. But in case of here, you have less registers. And the one thing what they need to say is here the emphasis on software. Here the emphasis is on hardware. Which means this point, what I need to say is the next. Here the software. Here I meant what is the compiler. Okay. So the first slide I had discussed, right? Since it is most of the instructions are of what a single cycle and it is going to be one byte, and if you want to achieve something, you need to write a code accordingly. But that's what I'm saying. At a higher level, we are not worrying about it. Just like that, we are writing the program. But who is actually converting to the object code? The compiler is doing it. Okay. When you have a minimal number of instructions, here, right, the number of instruction class is reduced. So when you have a minimal number of instructions, without instructions, whatever the task we have given, that has to get achieved. So the emphasis, which means, right, it is very hard to design a compiler for the risk based compiler. This is what we are saying it. The emphasis on a software is the sense. So it is very complex in defining sir class sir. ஒன்றும் பண்ணுங்க சார். Okay, so here, right, we have an emphasis on that. That means the complex in designing, not defining. So there's a complex in designing a compiler. But when you take as a solutions, here, right, writing a compiler is easy for system because all those complexity will be move on to the hardware part. So hardware is going to do on behalf of the, whatever we are trying to do, hardware is going to do it. But here, in case of risk, what is happening is the compiler, right? It will has to do it because we have only the reduced number of instructions. With the help of that instruction, the task has to get achieved. So compiler will have to optimize all those things, and accordingly it has to give. So that's why, right? Normally, they will put up this word when you go with the risk-based machines. Emphasis will be on software. Here, the software is designing a compiler for risk-based is much complex compared to the risk-based machines. But here, right, hardware part. Okay, so hardware is taking all the responsibility because here something is called micro programming. Some approach is that like a micro programming. So wherein, right, what the risk-based machine will does is it will take some instruction like 6 byte, assume 6 byte instruction it will take, and it will split up. It will split and accordingly it will execute. So all those things will be carried out in the hardware. But in case of here, right, in case of software, this 6 byte has to be carried by the compiler itself. That's what I'm saying. Okay, since we have a micro programming concept in hardware, in CISC, hardware will take care of these responsibilities. But here, in case of risk-based machine, compiler has to be done. So that's why here emphasis will be much on the software side, and here there emphasis will be much on the hardware side. And the one more word you might have heard is sorry. Have you heard this word? Architecture, load store architecture. Did you heard this word in the previous semester? Very important. Have you heard? Yes or no? Binary answer தான் கேக்குறேன். நான் what is in கேக்குறேன்.
Load store we heard.
Load store?
We heard, ma'am.
You heard. Oh, very good. Now can
LDR, STR.
it's an
Instructions we
instruction,
have
right?
learned,
Yeah.
ma'am. Yes,
LDR,
ma'am.
STR are the instructions.
Instructions we have learned, ma'am.
Uh-huh.
This one we don't know, ma'am.
Don't know. See,
Only how to write instructions we have learned.
okay. So when you just listen, when it is a load store architecture, RISC is a load store architecture. Why it is whatever the data processing instructions we are doing it, because we are what is ALU? It's an arithmetic and logical unit, right? So when you are any arithmetic and logical operation we are performing in a RISC based machines, so solely, right, it will carried out in register only, which means I gave an example, right? So suppose we have this add R0 comma R1 comma R2. So what is happening? What about the operands? All the operands are what?
Registers.
Registers. Clear? But when you take a CISC based machine, when you take a CISC based machines, so you have this add AX comma 3000. I have this option. So one operand is what? A register operand, other operand is the memory operand. So it will work like this. So whatever the operand I have, AX plus the data in this location will be added and it will be stored to the register AX. But when you just go with this load store architecture, so all the operands should be in registers. So but the data is where? One data is at 3000, other data is at 3004 something. Okay, so but AX, this has to be there. Move AX comma 3004. Okay, so from 3004 we have moved, the other data we have added directly. But here, right, we have to load the data from 3000 and again we have to load the data from 3004 and then, right, we need to add it. You got it? So which means, right, all the arithmetic and logical instructions in RISC-based machines will carry out the operation in the registers. That's why, right, this architecture is called the load store architecture. Why it is load store? Before performing any operations, it has to get loaded into the register. After performing the operation, it has to be stored back to the location. So that's why, right, RISC-based machines are load store architecture. Clear?
Yes, ma'am. Yes, ma'am.
Understood what is clear. Okay. So this what all about risk and the risk based. So keep remember. I mean, though I explained all those things, currently you keep remember what is microprocessor and what is microcontroller. It's a general purpose. It is an application specific, and this is off chip and this is on chip. And other than that, this is a common things. When you learn about any processor or microcontroller, these are all the things that are very essential. Just for any processor or microcontroller you are going to learn. The next one is the RISC and CISC based architecture. So as I told you, right, nowadays all the processors have been moved to the RISC based architecture. The reason behind it is what? It is mostly the power efficiency. Okay, because you yourself can control now, because when you take a CISC, I told you, right, all those things is going to be done by the hardware. When something is done by the hardware, so probably, right, will it require more energy or not? Yes or no?
Yes,
Yes,
ma'am.
yes, it is going to be done, because the next, right, we are going to read about parallel, instruction level parallelism, data level parallelisms, all those things we are going to do it. Okay, so we are going to do it how to write a code by to achieve all those things. But when you take an Intel, right, Intel is doing on behalf of us. So we have put the burden to the processor, and the processor is doing on behalf of us. But when you just go with the compiler, when you go with the RISC-based machines, we also have to do all those things, and accordingly, right, we need to give an input to the RISC. So that's why, right. So if they are claiming that RISC-based machines are optimized in terms of energy consumptions compared to the RISC-based machines. And we have seen proof of like all the processors that are there in your mobile. You might have seen, right, Cortex M3, M4, or A series, Cortex A series is also there. So it's a difference. When you just go with M, it is for like mobile oriented applications. When it is as a series, it is for application. That's a processor. Okay. When it is a M, right, it may be used for embedded oriented kind applications. So that's the difference. Okay. Now, right, I will come back to your syllabus. With respect to your syllabus, I need to ensure that though we have talked risk, all those things, in the syllabus, what we are going to, I mean, not syllabus, the textbook, right? We are supposed to follow the textbook. Something. What is that name? Yes, this is the textbook. I think I forwarded a link to you. It's a computer architecture, a quantitative approach by Hennessy Patterson, right? Yeah. So this is the textbook. I have forwarded the link. Um, Computer architecture. Almost all the 4 units is going to get covered by this book. I need to say, like, first 3 units, it will be interesting one, and when you just go with the 4th unit, again it's going to be a kind of theory. Uh, but first 3 units will be easier. Okay. Uh, the examples what they have taken in this textbook is they have gone with MIPS architecture. It is like, it is not an ARM. Okay. It's not an ARM based architecture, but it is a RISC based machine. MIPS 64, it's a RISC-based architecture. It is not an ARM-based architecture. So all the examples that have been covered in our textbook, this textbook, it's a MIPS 64-based architecture. It's another processor, that's it. But it is a RISC-based architecture. So maybe, right, the registers, it may be slightly varied compared to what you learned in computer organization, because in computer organization you learned about ARM-based things. And keep remember, I told you on the day. So when you just have an ARM, right, ARM people, they are not developing their own chip, not developing the physical chip. Okay, they are not developing the physical chip. Instead, what they are doing is they are giving the IP code. So what is IP? It is an intellectual property. So IP core is the intellectual property. So the people who are on to developing RISC-based processor, okay, who are on to developing a RISC-based processor or a microcontroller, what they will do is they will get this IP core. So you have this IP core, and whatever they needed, IP core is what? ARM core. Okay, when you talk as IP core, which is nothing but the ARM core, they will get this IP core, and whatever the devices need external devices they need, they want D2, D3, D4, they will interface and they will try to deliver the product. This is what happening with respect to ARM. Okay, understood? ARM, they are giving the only the intellectual property core, and the core is get by the manufacturers, the who is developing the physical chip, and whatever their requirement, they are fixing it up and they are delivering. See, why I'm saying this is maybe, right, few may be interested to work with IoT or whatever the things, because when you take a Intel processor, um, irrespective of the manufacturer, if you learn about Intel processor architecture, it is more than enough to write a programming, low-level programming. I'm speaking about only low-level programming. So it will be the same with respect to Intel processor. But when you go with the ARM-based thing, what happen is, see, assume that this is some Philips people. They got something, they will get the code, and they will add whatever the devices they need, and then they are delivering. Assume some other people like Atmel people, if something example I'm saying, say some X people, they will get the same IP core, but for their need they may assume that they may integrate some other devices, and they are developing, and they are just exporting the chip. So now what happened is, when you are going to use any microcontroller based on ARM, what it is completely vendor specific. It is not a generalized case, because in case of Intel, when you go with Intel, if I'm reading, assume for example, if I'm reading 8051 microcontroller, if I read 8051 microcontroller, throughout whoever is developing, it is going to be the same. But it is not in case of ARM people. Okay, because ARM is giving, and whatever they need, they are fixing up some devices and they are delivering. And so that's why, right, when you are going to use ARM based microcontroller in your project or all those things, it is very much essential to read the data sheet. Only if you read the data sheet, then only right you can work with these things. Or else you can't do anything. Got it? So you don't have any textbook. So that's what I try to say. Because when something is common, so probably right we may get a textbook, but this is not the case with respect to the ARM-based microcontroller, because we have plenty of vendors. Each vendor they can interface their own device and they can do anything they want. So probably right. So if you plan to decide some microcontroller based on ARM based microcontroller you are going to use in your project, you need to go with the what? Data sheet. You have to read the data set and accordingly that you have to proceed. Okay? That's the thing. And all the stories just for your knowledge, I am just saying it. But in your textbooks, right, we are going to see about MIPS 64 architecture. It's a RISC-based machines. So all the examples are based on this. So from tomorrow, we will start with this. Okay, I mean, actually, we'll get into the syllabus. I just because I need to, I want these introductions to be known to you. So that's why I covered up today. So tomorrow onwards, we will get into the syllabus. So till then, if you have any doubt, you can ask me. With that we will wind up this class. And any doubt, you can ask me. Everything, or you haven't understood anything?